Okay, so let's solve another problem. So this problem is about rotational motion, but now we are not only interested in the angular characteristics of this motion, we are also interested in the total acceleration of point B. Point B is also rotating, so it's rotating around point A. Here radius of rotation is not shown, so we need to actually draw it. Right, so it's right there. So this is that radius of rotation. So this is 4, so this is 3 meters, right? So then our radius of rotation BA is equal to 5 meters. Okay, so this is good. So let's calculate all those angular characteristics. So we have the counterclockwise motion, also acceleration. That means we have also counterclockwise acceleration here as well. Right. Initial angular velocity is 10 rpm, right? And let's convert it right away to radians per second. So we have 2 pi radians in 1 revolution, and then we have 60 seconds in 1 minute. So this is equal to 10 multiplied by 6.28. So we are taking pi number after the third significant figure divided by 60, and this is 1.05 radians per second counterclockwise, right? And then we have our final velocity 40 rpms, and this is 40 multiplied by pi divided by 60. So this is you could actually like multiply this by 4. 6.8, right? So it's 4.19, right? So 4.19 per second also. Likewise, so then we can write that final velocity is equal to initial velocity plus, because we are accelerating, alpha multiplied by t. So our angular acceleration is equal to final velocity minus initial velocity divided by t. So this is equal to 4.19 minus 1.05 divided by 5. And this gives us how much? Let's see. So it's 4.19 minus 1.05 divided by 5. 0.628 radians per second squared, and this is also counterclockwise, right? Okay, so let's right away calculate normal and tangential component. We have two components of the total acceleration. So we have a normal component, so which is responsible for the direction change. So our point B is moving around like point A, following the circular trajectory. So it's always like changing velocity direction, right? So the velocity at this point B is always like changing the direction. So that normal component, it is responsible for the change of the direction, so how fast this point is changing the direction. And then the tangential component is responsible for the magnitude of this velocity vector, right? So it is showing us so how fast the magnitude is changing, right? Okay, so our normal component is equal to magnitude of the normal component, so it is equal to omega squared, right? Multiplied by the radius, Okay, so which is this. Okay, and this is equal to omega squared. So this is that final velocity after 5 seconds. So it is 4.19 squared, right? Multiplied by the radius, so which is 5. Okay, let's see how much is this. 4.19 squared multiplied 5. Okay, so 87.8. So it is 87.8. And this is meters per second squared. So this is the magnitude. So for we are not dealing with the vectors. We are not dealing with directions. So for we are calculating. So we are calculating our components. Okay, and then tangential component, it is equal to alpha multiplied by r. Alpha is 0.628 multiplied by 5, and this is equal to 0.628 multiplied by 5, and this is equal to 3.14, right? So 3.14 meters per second squared. So we can calculate magnitude of the total. So since so this is tangential, so it is perpendicular. It is perpendicular to the radius, and it is aligned with the radius. So we can calculate it as square root of normal squared plus tangential squared, right? And this is equal to, so about the same, right? Because this is extremely small relative like to this, so we should expect to see something close to this, right? 8 squared plus 3.14 squared. Okay, and this is equal to, let's calculate this. So we have 87.8 squared plus 3.14 squared, and square root of this 87.9, right? So 87.9, as we can see, it's quite close to this as we predicted. 7.9, a little bit longer meters per second. Okay, so we've got the magnitude, right? So we've got the magnitude of that vector. So now we need to work with direction, right? So we need to work with direction. Okay, I actually did magnified schematics here. So let's use this one. So let's maybe move it a little bit here. Okay, so let's draw this radius. Okay, so then let's draw our normal component, so which is going to be extremely long, right? So it's going to be here. So this is our normal component. Okay, so then we will draw tangential, so which is going to be much shorter and perpendicular to our radius. So this is tangential, and it is aligned, right? So it is aligned with the angular velocity because we are accelerating. And so somewhere here, right? So somewhere here. So now let's draw resultant, and this is going to be total acceleration, right? So result of addition of these two vectors. So here, let's maybe draw it with this color. Okay, so and this is going to be our total. So this is a total. So this is the total vector, total acceleration vector. Okay, so now the only thing is the direction, because we already know, right? So we already know magnitude. We just need to define direction. Okay, so let's think how we can do it. So let's maybe draw a horizontal line, so which is going to be our reference, let's say. Okay, so let's see, right? So let's see how we can better do it. So we can calculate a couple of angles. For example, we can calculate this angle here, right? So this angle alpha, and this is going to be our angle beta. Okay, and alpha plus beta, it's going that sum is going to give us like that angle relative to the horizontal line, which will define direction of our total acceleration, right? Okay, so alpha, so this is 4 meters, right? So, and this is 3 meters. We can calculate tangent of this angle alpha, and tangent of this angle also alpha is 4 divided by 3, right? So 4 divided by 3. So then our angle alpha is equal to, so let's calculate it. So it is 4 divided by 3, 53.1, 53.1 degrees, and then b sorry, like beta, so tangent of angle beta is equal to tangential. Tangential is what? So tangential is 3.14, right? So it is 3.14 divided by normal, so which is 87.8, right? So 87.8. 87.8. Okay, so then our angle beta is equal to 3.14 divided by 87.8. Okay, and then let's take the tangent, 2.05, right? So 2.05. Okay, good. So then the total angle, so alpha plus beta, is equal to 53.1 degrees plus 2.05 degrees. Be careful with those degrees, because if you don't show degrees, by default, those are radians, right? So, and this is a completely different story. Okay, so 53.1 plus 2.05, and this is 55.2. So 55.2 degrees. Okay, so we can write down our answer. So our total vector is equal to 87.9, 87.9 meters per second squared at 55.2 Okay, so as you can see, again, like this problem is not that complicated. It's very straightforward. So, but you need to be careful. Don't forget that you need to not only define the magnitude of the vector, but you also need to define the direction. And again, like here, we are just defining direction with the angle relative to the horizontal line or vertical line, whatever we like.